In this video, we're going to discuss calculating delta G naught, the standard change in Gibbs free energy for electrochemical cells. As a way of looking at this, let's do an example. So if you have a cell consisting of aluminum in its 3+ oxidation state and copper in its 2+ oxidation state, and if you go look up the reduction potentials for these, for aluminum, it is negative 1.67 volts. And for copper, it's positive 0.34 volts. So to find the cell for which the thermodynamically favorable reaction occurs, we need a positive E naught. So we're actually going to flip the sign for aluminum and make it get oxidized. So instead of reducing, aluminum is going to be oxidized. It's losing electrons. And that gives us an E naught oxidation of 1.67 volts. Notice that to balance this reaction equation, you have 2 electrons being consumed on the reactant side and 3 being produced on the product side. We know that that's not allowed because that somewhere here you're creating an electron. So in order to get 2 and 3 to balance, we always bring both of those up to 6. So we're going to multiply this top part here through by 3. The copper reaction, and the aluminum reaction we're going to multiply through by 2. So for the copper, that's going to put a coefficient of 3 here, 6, 3. For aluminum, it's going to be 2, 2, 6. Now we have the same number of electrons on both sides. That satisfies the law of conservation of mass, so that's fine now. So our overall reaction here, first off, let's calculate our overall E naught. That's going to add up to be 2.01 volts, and our overall reaction is now going to be 3 coppers ions in solution plus 2 aluminum. It's going to be solid aluminum, yields 3 copper metal plus 2 aluminum ions. All right, so that's going to be our overall reaction. That's going to make aluminum the anode and the copper strip the cathode. All right, so these are all things we've done before this to find the reaction equation, which matches up with the positive E naught. Now, what we have not said is why this is the case. The reason it's the case is because it turns out that this is the reaction for which there is a negative delta G naught. The equation for this is that delta G naught is equal to N, which we'll define in a moment, times a constant called Faraday's constant, times the E naught value. These numbers are both positive numbers. If you plug a positive number in for the E naught value, you get a negative delta G naught, and we know that that means a favorable forward reaction or a reaction in which there's a greater concentration of products at equilibrium than reactants. So that all kind of makes sense that we know that the reaction that occurs is the one with the positive E naught, but now we know why. It's because when you plug in a positive number here for E naught, you get a negative delta G naught. All right, now how would we actually do this for this reaction? The first thing you have to know is what all the letters stand for. N is the number of of moles of electrons transferred in the balanced reaction equation. In this case, the number of electrons transferred is 6 because of all the reasons that we went through just a moment ago to get the reaction to balance out. So in this case, it's 6. A lot of the examples we've done involve 2+ ions because they're quite common for transition metals. And so in those other cases that we've done in the past for, say, a zinc and copper cell that we did in the previous videos, that N value would be 2. F is Faraday's constant. It is 96,400 coulombs per mole. And it turns out that this is going to be the unit that's going to give, this coulombs unit is the amount of charge. This is the charge unit in the SI system. The 96,400 is the charge on a mole of electrons, essentially. So this is going to be the number that's going to allow us to transfer back and forth between volts, which we can measure in the lab, and joules per mole, which is what we want to have our units for delta G naught. So when we plug these in, delta G naught is going to be negative 6 times 96,400 coulombs per mole times the voltage, which is the 2.01 volts that we calculated just a moment ago. It turns out that when you have coulombs times volts, that's going to result in the unit being joules. So the number we get out of this is going to be in joules over moles, which you have to watch out for because we're used to dealing with delta G naught in kilojoules per mole, but this answer is going to come out in joules per mole. So we do 6 times 96,400 times 2.01, and that gives us this rather large number, which I'm going to go ahead and divide by 1,000 to express in kilojoules per mole. So delta G naught is going to be negative 1,160 kilojoules per mole. Okay, notice that I divided by 1,000 to get joules into kilojoules, all right? So you could have left it in joules, that would have been totally fine. But notice again that we have a negative delta G naught, which corresponds to a favorable forward reaction, which jives with our previous understanding that E naught has to be a positive number, right? So anytime we're trying to calculate the delta G naught value for a cell, we're going to do the problem exactly the same as we normally would to get our E naught value. That E naught value is going to plug into the yet another delta G naught equation that we have. The trick here is you're going to have balanced the reaction ahead of time so that you know what N value to plug in here. However many electrons are transferred in the reaction is going to be the N value. F is Faraday's constant, which we're always just going to we're always going to have available to us, and times the potential, which we've already calculated.